Hey everybody, I want to use this video to show you how to do a chi-square goodness of fit test. So let's go to the notes and I'll show you how to do that. Where are my notes? There, sorry to hide them from me. All right, so this is where we left off in the last video. I'm going to assume, by the way, that you watched the introduction video explaining what this calculation is, and then we're gonna do that calculation here. So here's a goodness of fit test. So the idea of a goodness of fit test is the thing I was explaining in the intro video, which is we're going to have a statement, a null hypothesis of the proportion of data that we expect to fall into each category, right? That's the null hypothesis. Proportion in category 1 is this, proportion in category 2 is this, proportion in category 3 is this, etc. And then the alternative hypothesis is really straightforward. It's just not that. Right? It's the population distribution is not that thing that we just said, it's something else. Now, we're not going to make any hypotheses about what the alternative hypothesis doesn't say anything about what the proportion in any given category is, only what it isn't, right? And so it's just population distribution is not the thing we mentioned up here. So my example is going to be this. It's going to be this test right here. So let's say that we have an old test, or we have an old study that says Americans' eye colors follow this percentage, and we're going to do a test and see if our data agrees with that or not. So let's do it. So here's how we're going to do that. So here, let's get a whiteboard going. Yeah, let's get a whiteboard going. So come on. It's always a struggle with the newer version of Zoom here. So we're going to have, I'm going to make this bigger. I want a lot of room to write here. So we're going to have hypotheses that look something like this. My null hypothesis is going to be that the proportion of blue is a certain number. I think it was 37%. Proportion of, I forget. I've forgotten everything. I got lost in the Zoom controls. 37, 18, 14, 31. That's blue, green, light brown, and dark brown. Okay, I'm going to call it PB, PG, PLB, and PDB. Blue, green, light brown, dark brown. I'll probably have to come back here when I immediately forget all these numbers. Man, getting old is rough. Okay, let's go ahead. I'm gonna get rid of that. There we go. PB, PG. I need to write P sub. Go away. P sub G was some number. P sub light brown LB and P sub DB DB. I believe this was 14, 18, and 31. Did I remember that right? I think this one's 31. I'm pretty sure about that one. 31%. And then I think they were 14 and 18%, but I'm going to go look just so I don't mess up my own example. 18 and 14, I had them backwards. Okay. It's 18%. This was 14%. Okay. So my alternative hypothesis is very straightforward. It's literally that thing I wrote on the notes, HA, the population distribution and you could probably just drop the word population there if you wanted to, just the distribution of eye color. Distribution, come on, of eye color differs from H sub 0, or the distribution given in H sub 0, I probably should say, but I'm not going to just for space. All right, so we've got that. Those are our hypotheses, and so what we're going to do is this. We're going to do chi-square. Chi-square is this. It's the sum of O minus E, observed minus expected, squared over expected, over all the cells. So the first thing we have to do is we actually have to calculate the observations before we can know, or before we can excuse me, calculate the expectation before we can do any math here. So our expectation, so the way you want to do that is the following. I briefly explained this in the other video, but if we survey 300 people, which is our total, right? That's our N. And it is true that 37% of all of the population that we surveyed had blue eyes, then we would expect that 37% of the 300 would. So I'm going to do 37% of 300, 18% of 300, 14% of 300, and 31% of 300 to find the expected values in the categories blue, green, light brown, and dark brown or black. And then we're going to compare those to the observed counts using that formula that we had. So let's go ahead and calculate the expected values first. So expected blue. So if 37% of 300, so I'm gonna show you a little trick here, by the way. So we're gonna do 37% of 300. And then the way we would do that is the following. We would do, that's 0.37 times 300, which you absolutely can just type into a calculator if you want to, but I'm going to show you another way to do it. So I'm going to think of that like this. This is 0.37 times 3 times 100. Right, so 300 is clearly 3 times 100, and then this 100, I'm going to rearrange this so that it does this 0.37 times 100, and I'm going to do that first, and then times 3, because the 100, all that does is move the decimal, so that makes this 37. So I get 37 times 3, which I don't know if you can do 37 times 3 in your head. If you can, you'll find that it's 111, and the way I'm doing that is that 30 times 3 is 90, and 7 times 3 is 21, so I'm adding up 90 and 21 to get 111. 1, 1, 1. Right, and so we can do that, do a similar thing for all the other. Sorry, I apologize. My Zoom is popping up on me here, or my Zoom folders are telling me I have videos done. And then we can do this for all of them, right? So really, this ended up being 37 times 3. And all the other ones are going to be the same, right? I'm going to do 18 times 3, 14 times 3, and 31 times 3, and those are all relatively easy. So my expected count for blue was 111. Let's go to the next one. We have 18, 14, and 31. So my expected count for green, we got 18 times 3 is 54. Light brown, LT brown. We have 14 times 3 is 42. I don't know why I used an X above and dot down here, but there you go. Dark brown. We got 31 times 3 is 93. So those are our expected values, 111, 54, 42, and 93. And I'm going to use the formula that we had on the other page. I'll just write it here. So here's where I'm actually going to use it. Sum of observed minus expected squared over expected. All right, we're going to do all that. So what we need to do is go find our observed values. Those are not, we don't calculate those, they're written in the table. So we're just going to use the ones in the table. So observed, get them over here so we can use them. Blue, green, light brown, and dark brown. I remember the first one, we had 97. I don't remember what the other ones were, so let's go look. 59, 56, 88. All right, let's go put those back. 59, 56, and 88. Okay, so our chi-square looks like this. Chi-square is observed minus expected. So our observed from blue was 111. excuse me, our observed from blue was 97. Our expected from blue was 111 squared over expected, plus observed of 54 for green minus expected of, excuse me, observed, I got that backwards, gosh darn it. I apologize. Let's get that correct. Our observed was 54. No, 59. It's 59, like I said, 59 minus 54 quantity squared over expected, which was 54, plus, so this is normally all be on the same line, of course. Our observed value for light brown was 56, minus our expected value of 42 squared over expected, which is 42, plus our observed value of dark brown, which is 88, minus our expected of 93 squared over our expected of 93. Pardon me, I'm gonna pause for 1 second here. Oops, no, that's not the right pause button. Sorry, had a sneeze there. All right, let's get back to the whiteboard here. All right, so we've got this right here, and I'm just literally going to jam this into a calculator. Right, that's all I'm going to do. So let's go look at that. Calculator. So what I'm going to do here, so I've got my calculator as always. I'm just going to literally type in that thing that we just did. So we had an observed of 97 minus an expected of 111 squared divided by expected, plus we had an observed of 59 minus an expected of 54 squared divided by the expected, plus an observed of 56 minus an expected of 42 squared. I did times there. I always hit that button wrong. Minus. It's all going to be divided by the expected 42 plus observed value of 88 minus an expected value of 93 squared divided by the expected value of 93, and we get a chi-square value of 7.16. So there you go. That's our test statistic. And you might say, is that number big or small? Excellent question. So here's how we can tell. Let's quickly pop back to the notes. So if you remember, our mean is equal to the number of degrees of freedom in this test. Or that's just true for chi-square in general. So the mean is equal to the number of degrees of freedom. For this test, though, the number of degrees of freedom is k minus 1, where k is the number of categories, and we've got 4 categories. So that means we have 3 degrees of freedom, and we got a test statistic of 7 point something. So is that big? It's big, but I wouldn't describe it as huge, right? So that's some indication that we want to reject our null hypothesis, but we'll see how much in just a second. So before I actually calculate that, let me draw out a chi-square distribution, because I realize now that I have not done that yet. So chi-square distributions are not like normal distributions. They're shaped a little bit differently. They don't go below 0. Like if you remember from the last video, we discussed why they can't be below 0. They go like this and then off to infinity to the right. Now, if you get a large enough number of degrees of freedom, chi-square distributions do look like normal distributions. The usual cutoff for that, I believe, is 90 degrees of freedom, which we're not even close to here. We've got 3 degrees of freedom in this case. And so our mean here is 3. And I will point out something. This chi-square distribution is skewed to the right, as are all chi-square distributions. So that means that the mean is to the right of the median, and it's also to the right, in this case, of the peak. So let me move my toolbar around here. So we've got, this is chi-square with 3 degrees of freedom. That means that our mean, which is here-ish, is going to be 3. And what we got for our test statistic was 7.16, right? 7.16. So that means that all this area to the right of 7.16, all this area represents all the samples that have a chi-square statistic of bigger than 7.16, which is to say they are more extreme, they are further away from our hypothesized population distribution than our actual observation. So that means that's where we calculate the p-value. That's the part of the graph that represents the samples that are more extreme than the one we actually saw, which, if you remember, the definition of the p-value is it's the probability, assuming the null hypothesis is true, that you would get a sample like the one you got or one that is more extreme. Well, here is the one that we got. There are the ones that are more extreme, and area probability equals area. So this area is what we want to find. That's our p-value. P-value is this area here. So the way we're going to do that is there's a CDF function in your calculator for chi-square. So that's what we're going to use. So let's go share that up. So if I go to the same place where you find all your CDFs, which is second bars or distributions, there are distributions here. Lo and behold, chi-square CDF, just like I said. So the format for this is lower, upper, and degrees of freedom. It's exactly like it is for t-distributions, right? So you identify the chi-square distribution by the number of degrees of freedom that it has, and then you tell the calculator what area in that distribution you want to find, right? So I want to find a lower end of 7.16, and an upper end of infinity, so some huge number with 3 degrees of freedom. And we find out what that number is, 0.0669. So about 6.7%. Right, so not a huge p-value, not a tiny p-value. It is slightly larger than our cutoff p-value of 5%, so we're not going to reject the null hypothesis here. So let's go write that on our whiteboard. So this p-value is, if I do chi-square CDF of 7.16 up to infinity with 3 degrees of freedom, we get something about equal to 0.0669, which is greater than 5%. So we are not going to reject the null hypothesis. Don't reject. That's not at all the right word there. Don't reject H naught. Right? This is almost enough evidence to reject the null hypothesis, but not quite. So let's go to the next page and write a conclusion. So my conclusion is that since we are not rejecting the null hypothesis, actually, let me go back here. Since we're not rejecting the null hypothesis, remember that the idea is we're trying to determine, we have this hypothesized distribution of eye color for Americans. And our alternative hypothesis is that the population distribution is not this. Well, we don't have enough evidence to say that the alternative is true. So we're just going to go default to the null hypothesis. And that is that the proportion of blue eyes is proportion of Americans with blue eyes is 37%. Proportion of Americans with green eyes is 18%. Proportion of Americans with light brown eyes is 14%. Proportion of Americans with dark brown eyes is 31%. Right? And so you can write that all out if you want to. I'm just going to sum it up like this. I'm just going to go here and say that we conclude, or this data suggests, data does not provide enough evidence. Doesn't provide enough evidence to suggest the distribution, pardon me, everything's in the way here, distribution of eye color among Americans differs from the old study. Right. So we don't have enough evidence to suggest that that other study that provided these percentages was wrong. We basically think they're right, but we're going to say it in a statistically hedgy way where we say, well, we don't have enough evidence to say they're wrong, so we just sort of leave it unstated that we think they're right. It's always a little unsatisfying, but that's the way you do it. All right, so let's go back and look at the test. I believe that was all the questions I asked, I think. Oops, where are we at here? Down here, right? So, right, appropriate hypotheses, we did that. Calculate the expected counts. That was the percentages. Percentage times the sample size. We calculated all these things, add them up to find chi-squared. We sketched the distribution, shaded in the p-value, use the CDF to calculate our p-value. We had our decision to not reject the null hypothesis and wrote our conclusion. So I'm feeling pretty good about this hypothesis test. And I think that's really all I want to say. So, yeah, I think that really is it. I'm not gonna mess around any longer. I'll just go ahead and stop the video here, and I will see you in the next one where I'm going to spend like 95% of the video explaining independence tests, and then I will briefly explain homogeneity tests and show how they are mathematically identical, but tell you about like the little semantic differences between them. So it'll be mostly independence tests, and then me saying, and homogeneity tests are like that, except in this one small way, so you just do them the same. All right. Anyway, that explanation aside, I will go ahead and see you in the next one.